Hello friends, welcome to Electronic Circuit Hub. So today I'm going to show you about the 1000 volt output No-Opto coupler isolated flyback converter design and simulation in LTSpice. Okay, so in order to design this circuit I have used LT8304. Okay, so our input is 24 volt and our output is 1000 volt. That is what we are doing. We are designing the circuit to get the 1000 volt output by using the flyback converter. Okay, so if you go and look at the data sheet of LT8304, so it has 100 volt input, micro power No-Opto isolated flyback converter with 150 volt 2 ampere. Okay, so if you look at the feature, it is 3 to 100 volt input voltage range, 2 ampere 150 volt internal DMOS switch. It has very low quotient current and it can work in the quasi resonant boundary mode operation at heavy load. And you can see it has internal undervolted lockout circuit, and it has also the short circuit protection, soft start, etc. Okay, so let us understand how you can design this circuit. So this is the basically the input side V in I have given the 24 volt. Then you see I have connected two capacitors C2 and C3, and if you look at the input signal, it is connected to the 24 volt, and if you look at the enable pin, it is connected to also the 24 volt. Okay, and this INT VCC is, you can see that it is connected to a capacitor C1, that is 1 microfarad, the capacitor and the ground, right? So I would say there is a mistake here. Let me correct this circuit. Okay, so the first, it has to go the ground, then it has to connect with the ground, right? So now at this side, this is switch pin. So switch pin is connected to the resistance R3, 100 ohm, and a capacitor C5, and the capacitor C5 is connected to the input voltage. And at this point, you can see here the RFB pin is connected to the R2, and the reference pin is connected to R3 and C4 in parallel, and this is TC, that is left floating. Okay, and now you see your switch pin is connected to a primary winding of the transformer, and the value of this primary inductance is 65 microhenry, and I have also connected the leakage inductance of the transformer. And if you look at the secondary side, the value of L2 is 1450 microhenry, L3 is 1450 microhenry, and L4 is 1450 microhenry, and you see the diode D1, D2 and D3 are connected for rectifier purpose. Okay, and the coupling between primary and secondary transformer is 1. Let me correct it to maybe 0.99 or 95, whatever, because in the practical case it is not possible to 1. And if you see here, our input is 24 volt and we want to get 1000 volt output. So that is why I have connected this kind of transformer configuration. Okay, so you have one primary winding and we have three secondary winding. Okay, we have one primary and three secondary winding. So what I'm doing here is I'm distributing the output, since our output is 1000 volt, so I am distributing my output among these three windings. Okay, so by doing this, I'm reducing the stress to the transformer secondary winding, as well as I'm reducing the stress to the diodes, rectifier diode and capacitor. Okay, so D2, D7, D3, C7 both all are the same value. So whatever voltage we are getting across C6 would be same as C7, and that would be also same as C8. And if you add these three voltage source, you will get the 1000 volt output. And for this simulation, my output is 1000 volt, but I am drawing very less current at output. So that is why the load value is 1000 kilo ohm. So that is how you can draw or you can design your circuit in LTSpice. You can see here the input is 24 and we want to generate the output 1000 volt. So if you look at these diodes, I haven't connected any practical diode here. This is ideal diode, and if you want to choose this diode, you have to look at the current rating as well as the peak inverse voltage. Okay, so since we are getting here 3000 volt, so I would say 330 volt more than should your peak inverse voltage should be more than 330 volt here, D1, D2 and D3. Okay, and you can choose your capacitor based on your current requirement. So now what I'll do is I'll run the simulation and I'll show you the waveform at uh, different point. Okay, so if you see here, my transient time is 1 second, and I have since I have connected a transformer here, this simulation is taking very much time. So what I've done is I have already run the simulation before starting this video. So if you see here, at this time I am getting the stable output. Let me check what is the output. Okay, so if you see here, the output is exactly the 1000 volt. If you look at this point, if you look at this point here, I'm probing my cursor here and I can see the output is 1000 volt. Let me divide into the plot pane and let me show you the output current. So you can see here the output current like what. Let me show you the output current here. So my output current is very less. If I click on here, you see 1 milliampere. So this output voltage is 1000 volt and the output current is 1 milliampere. That is how it has been designed. If you see at this point, this is 1000 volt output, and if you see at this point, this is 1 milliampere output. Okay, what I'm gonna do is let me delete this trace. So delete this trace. Let me check the switch node voltage, right? So this is also important. So as you see, your simulation is running. It is quite slow because of we have used inductor in our design. Okay, let me voltage at switch node, how it looks like. If you should look at this is the voltage at switch node. If you try to catch one pulse, that is, this is your switch voltage across MOSFET drain to source, and if I see it's maximum 140 volt, it's not more than that. Your voltage at switch node is 140 volt. You can see here, that is how it looks like. Since it works in the quasi-resonant mode and your output is very less, that is how you can see there is a difference between two pulses. Okay, there is a quite difference between two pulses. Okay, so this is the voltage across switch node. Now let me show you the voltage across the transformer. So I'll click here and click here. So let me delete the switch node voltage, and this is the voltage across the transformer. You can see this is coming negative and maximum peak is around 130 volt. Since my first cursor was here and the second cursor was here, so if I place the cursor reverse, let me do it, because your positive side should be dot and negative sides without dot. If you look at that, you see this is the voltage across the transformer, primary winding of the transformer, that is 130. And let me show you the voltage. Let me delete this and probably yes, let me delete the output now. Yes, and let me show you the voltage across the secondary winding of the transformer. Okay, so this is the voltage across the secondary winding, and I see here the peak value is 331. Okay, so let me show you the voltage across another secondary. So let me check. If you see here, both voltages are overriding each other. Okay, so if you see they are exactly same, let me show you the voltage at third output. So you can see all the four waveforms are overlapping each other. Okay, so this is the voltage. Let me delete this. I'm gonna delete this. Yeah, delete this also, so that I can show you other waveform. Let me show you the diode waveform. Okay, so that is how you can see the diode voltage looks like. It has the negative voltage, peak inverse voltage, and if I say it's the negative is around 449 volt, and this was the voltage across the diode. And let me delete this, the voltage across the diode, and let me show you the voltage across the single capacitor. It is looks like that. It's a 328 peak and it has some ripple. Let me show you the voltage across C7. Let me show you they are overlapping each other. That means the voltage at C6 and the voltage at C7 are same. Let me show you the voltage at C8. So if you see the voltage at C8, it's also more or less same, but sometimes it's higher. It is bit higher. The inductance is same, but I'm not sure why the voltage at C8, the lower winding of the transformer, is higher. If I see it's around 350 volt. Okay, and let me click Q and show you the final output voltage. So this is the final output voltage, and it's, if you clearly see here guys, it's 1 kV. It has some ripple, but it's 1 kV. And let me show you the current here. So this is the current and it's around 1 milliampere. Let me show you the output power. So control alter, you will get power symbol. Let me show you. So our power is around, it's a peak around 1 watt. Okay, so guys, hope you understood how will you design the 1000 volt output with no opto-coupler, isolated transformer based isolated flyback converter for 1000 volt output, 1 milliampere current.